Let's do a calculation of fission, where we're going to let uranium-235 fission and supply energy for a small city. We're going to assume the average fission release is 180 MeVs. Don't take that as the correct number. I'm just using it for purposes of calculation here. 180 MeVs. We're going to say that an average home uses 11,000 kilowatt hours. Kilowatt hour is a unit of energy. We're going to say a particular city has 8,000 homes, so kind of a small city, 25,000 people or such. How many fissions do we need to supply the energy? What mass of uranium-235 is needed? And along the way, we'll assume 25% overall efficiency. That may be too high, but 75% being lost. And that's just for this particular problem. So one home, 11,000 kilowatt hours per year. If we switch from kilowatts to watts, that's a factor of 1,000. The watt is joules per second. So I'm going to kind of keep track a little bit of your cancellation factors. So joules per second for the watt. 3,600 seconds per hour. So I'm canceling off the seconds here and the hours. And we have a city with 8,000 homes in it. So this is the average home energy use, so we'll multiply by 8,000. And what I arrive at, and you should double check this, 3.17 times 10 to the 14th joules per year. 3.17 times 10 to the 14th joules per year. Now, how much energy do we get out of one fission? One fission provides us with 180 MeVs. Let's convert that to joules. 1.6 10 to the minus 13 joules for 1 MeV. So I'd have 2.88 times 10 to the minus 11 joules per fission. We're going to need a lot of fissions. 2.88 times 10 to the minus 11 joules per fission. So for the number of fissions, we know the joules per year that we need to have. We're going to divide by the joules per fission. So 3.17 10 to the 14th joules per year is needed. We're producing 2.88 10 to the minus 11 joules per fission. So the joule units will cancel, and we'll have units of fissions per year when this is finished. And again, you ought to check this. 1.1 times 10 to the 25th fissions per year. So that's the number of fissions per year. Now, how much mass of uranium-235 is involved? Well, we need one uranium-235 for each fission. So let's go ahead and start with the number of uraniums that we need. 1.1 10 to the 25th. Let's say atoms of uranium-235. And 1 mole would be Avogadro's number, 6.02 10 to the 23rd. That will give us the number of moles that we would have in our supply. And then uranium-235, roughly 235 grams per mole. So our atoms have canceled, our moles have canceled, and we have grams. Again, you should check this. 4.3 times 10 to the 3rd grams. So that's not taking into account efficiency yet. Let's go ahead and do that. I'm going to convert to kilograms. So this would be 4.3 kilograms worth of delivering energy out of these fissions. Is our efficiency 0.25 times the actual mass needed. So we have to divide by 0.25 here, and I came up with 17.2 kilograms. We need 17.2 kilograms of uranium-235 to supply this city with energy. Now, that's the, oops, sorry about the viewpoint here. So we found how much energy per year was required for all of these homes. We found the energy in one fission. We've divided the total energy per year by the energy per fission. That gives us the number of fissions per year. That tells us how many atoms of uranium-235 are required. We work through to find out how many moles of material we have, and then 235 grams per mole, and we get 4.3 kilograms. Now take into account the efficiency. We need more uranium-235 than just from the energy calculation, because we only get 25% of that energy reaching the customer. Now, I did another little calculation. It's not in the wording here, but what about if we use coal to produce this energy? I looked up and found that we get 40 times 10 to the third joules released from burning 1 gram of coal. 40 times 10 to the third. So we have our energy need here, 3.17 times 10 to the 14th joules per year. Let's divide that by 40 times 10 to the, I'm going to change unit here, 10 to the 6 joules per kilogram. We've got 10 to the third joules per gram. So if I convert this to kilograms, there are 1,000 grams in a kilogram. That gives us another 10 to the third power. So when I divide here, the joules will cancel. I have number of kilograms of coal I have to burn per year. And I came up 7.93 times 10 to the 6 kilograms per year. Again, this is not taking into account efficiency. This number, if we process it, 0.25 times the actual mass needed, we find that for the actual mass of coal, we get 3.17 times 10 to the 7th. I'm hoping, I just see something suspicious here. I see a 3.17 here and a 3.17 up here. I'm not sure if that's quite right. It might be going okay though. So you should check it. The steps up here are correct. I'm not confident about this last calculation. But that mass per year, if I compare that to the uranium, 3.17, if this is the correct number, times 10 to the 7th kilograms in 1 year, and the uranium 17.2, so 1.84 times 10 to the 6. We need about 2 million times more mass of coal than uranium to provide this energy. 2 million times the amount of coal compared to the uranium. There's much more energy in the nucleus than there is available in chemical reactions that deal with the electron structure around the nucleus. We need a lot more coal than we do uranium. But coal is more abundant than uranium. So talk to your economists, talk to your instructor, ask some questions.